Hello, SCD 114 students. I hope you guys are all doing well, and thank you very much for accommodating this year's very sporadic schedule with the holidays and conferences. We did fall a little bit behind. So, by using this recorded lecture opportunity, I'm going to try to catch us up as close as possible to the course schedule that we planned ahead of time. So last time that we met, we were going over the flour and flour mixtures chapter 17. We left off on slide 20, where we just finished discussing bread flours, cake flours, and all-purpose flour. So the next type of flour that we're going to discuss is our pastry flour. Pastry flour, you're not going to really find it in too many supermarkets. It's not really available retail. This is more of a wholesale product that you will find. It is mostly used for commercial bakeries. It is similar to cake flour, but a little bit softer than that. You're going to get a more tender product when you're using the pastry flour. Less gluten production potential. And we will see this for pastries and cookies. Following that type of flour, we do have our self-rising flour. Self-rising flour, you will find this in supermarkets. This is in homes and commercial kitchens. It does contain your leavening agents and a little bit of salt. So we're talking about our chemical leavening agents, such as our baking powder, where you would just add some sort of liquid, be it oil, eggs, water, so on. It's mostly used for our quick breads. If you want to really get to the nitty gritty of this, you'll see this with your pancakes, pancake mixes. But you can buy it on its own without any extra flavoring, and you can do popovers, you can do cream puffs, you can do cakes, and so on, just adding water. We do have some non-wheat flours that are commercially available. All right, so we have rye. Rye will produce a little bit of gluten, but not to the same effect that we're going to get from our wheat flour. So it does have a limited ability to make our gluten because it does contain glutenin and gliadin. Um, the glutenin, it just produces, it contains that in smaller amounts. So while it will produce gluten, it's not going to make it in the same amount as your regular wheat flour. Cornmeal does not have any gluten potential at all because the main protein is zein. Soy flour, it's high in protein, but there's no gluten potential there at all. Our buckwheat, this is the one that you want to be careful with. Buckwheat, remember, it is not biologically related to wheat, although it is buckwheat. There's no gluten making potential there. However, because of the price, you will see buckwheat. If you're looking for soba noodles, a lot of times it is mixed or diluted in a wheat flour mixture. All right. So you can get gluten there. So this is one of those ingredients, one of those type of noodles that you want to pay attention to what's in the ingredient list. Next is our triticale. Triticale is a cross between your wheat and rye. Um, Again, you want to be careful with this one because, again, celiac disease, some people have it worse than others. Some people are more sensitive than others. Triticale will produce gluten, but in limited potential. And then our potato flour, no gluten whatsoever. So you're good with that one. We have our treated flours. So our treated flours, they do improve functional properties. So our aged or unbleached flours, we can store those for several months. Bleaching, as with anything, as soon as it's oxidized or makes contact with oxygen, the color does become a little bit lighter, but it's not an actual chemical bleaching, so it still does retain a creamy color. Whereas maturing, the older that you are, sorry, the longer that you hold your flour, it improves the baking qualities because the proteins do tend to get a little bit weakened. They get older, they age, they're not producing as much gluten as a younger flour would. All right, so you get something a little bit more tender. As far as chemically bleached, we can force that with chemicals. Remember, anytime we lower the pH on something, it does get a little bit brighter or lighter in color, but this also speeds up the maturing effects. So it breaks down the proteins as well. Remember, we're working with proteins. And this one does tend to have a lighter color than our naturally oxidized bleached flours comes out with because we are forcing it. So when we're looking at our flour mixtures, all right, flour mixtures, flour, any sort of liquid. What else is going in there to produce cakes, cookies, crackers, breads, whatever it is? We're looking at different ingredients. So we're looking at our leavening agents. All right, leavening is just incorporating air into our flour mixture. We're looking at sugar, salt, liquid, fat, eggs, any commercial additives, and then our leaveners, be them biological or chemical. So the leaveners are only leavening. They're aerating our mixture. They're putting air into our mixture. It could be oxygen or it can be CO2. But we do this on purpose to get a little bit of height. It tenderizes kind of by adding air into our flour mixture, and it produces a light and porous product. So how do we leaven? We can leaven with either air, steam, or carbon dioxide. So by adding air and steam, we can do this physically, all right? We can whip, we can use the power of vaporization, biological incorporation of air into our product. We have yeast and bacteria. Every time we give them a little bit of food, they metabolize that and they create gases. And then chemical leavening, we have our baking powder and baking soda. Most leavening is accomplished by CO2. So you can look at these pictures right here, and we can see what leavening actually does. By adding air to it, we make it a little bit less dense. All right. And we get that height over here. You can see the unleavened and the leavened bread products over here on the left side. This is a tighter product. This looks very heavy, whereas this one looks a little bit lighter and porous. All right. Look at the crumb. All right. Remember, the crumb is the inside of the bread that we're looking at. The crumb that's well leavened over here, you've got your holes. They like vary in size and shape, but definitely not as dense as the one on the right here. So when we're using yeast, yeast is our live one-celled organism. All right. So we're going to mostly be working with Saccharomyces cerevisiae. All right. It is alive. We do want to feed it. We do want to nurture it. We do want to be gentle with it. It does need to undergo a fermentation process. So this is the one that you want to look at over here. To get the CO2, we're looking at it as a chemical formula always. To get the optimal amounts of CO2, we have to start out with yeast, some sort of food source. All right. Most of the time, any bacteria, their food source would be like some sort of starch or sugar. We do want to add a liquid and we want to keep warm temperatures. This over here, the yeast plus 6 oxygen plus glucose is going to give us 6 CO2 gas molecules. You don't want to memorize this right now. You just need to know what it is. So when we're fermenting yeast, all right, on its own with oxygen, we're going to come out with carbon dioxide and water. When we're fermenting without oxygen, we're going to end up with ethanol, which is alcohol, and our carbon dioxide here. So we've got different types of yeast available to us as consumers. We've got our dry active, all right, that's the most available one that we have. That's the one we have been working with this one in the kitchen. When you're reading a recipe, The recipe, sorry, the packets of yeast are standard across the board. One package is going to equal 1/4 of an ounce or 2 1/4 teaspoons, not tablespoons. We also have fresh or compressed yeast. You're going to want to keep this in the refrigerator. And then we have our instant dry active yeast. All right. All are available at the supermarket. I know during the COVID pandemic, everybody started making their own yeast. This became some product that was hard to find. It did become a little bit more expensive, but thankfully prices have gone down, and you can make your own bread at home without having to scavenge your yeast products. When you're activating your yeast, all right, remember it is a live organism. You want to treat it very gently, all right? So for optimal fermentation, to like wake it up and like hydrate it, you want to keep the temperature between 81 degrees Fahrenheit and 100 degrees Fahrenheit. Anything higher than that does have the potential to kill it or inactivate it. You don't want to go too harshly with the temperatures. When you're looking to do your own yeast mixtures, what you want to do is just run the hot water at the sinks in the kitchen. Um, when you're yeah, run your hand underneath the water. When the temperature feels like the same as your body temperature, that's when you know you're good to go. If it's too hot for you, it's too hot for the yeast. So anywhere between 81 and 100 degrees Fahrenheit. The other product that you guys probably worked with when you made your sourdough was a starter. All right. We have our harmless bacteria that mixed with liquid and the starch does create CO2. All right. So you can create a starter that you can feed along the way. You just keep on adding a little bit of flour, taking out some water, and back and forth. You want to keep it alive. This will give us a sour flavor. If you ever had your sourdough breads, there's people out there that have had starters going for at least 20 years or more. It's got different types of bacteria in there. The bacteria creates different types of acids, so you get that sour flavor, but it's not rancid. All right. So we use this in our sourdough bread, in our cheese, and some alcoholic beverages. Um, Again, this is very classic to our San Diego sourdough breads. Chemical leavening, we have baking soda and baking powder. All right, the difference between the two, baking soda is only sodium bicarbonate, whereas baking powder is sodium bicarbonate or baking soda with a little bit of acid, and it's got cornstarch in there. When we add liquid, we do get the CO2. So if you've ever done the volcano science experiment in junior high school, this is exactly what you use. Baking soda, a little bit of vinegar, all right? And then you get that explosion. But what do we have to remember with this? Baking soda is alkaline. When we add the acid or the vinegar or whatever we're using, it can be tartaric acid. Tartaric acid will neutralize the alkaline. So we have something that's alkaline, something that's acidic. We want something in the middle. Remember, acid will bleach. All right. So when we're looking at, we're going to do this experiment in the foods lab. We're going to make a chocolate cake and we're going to make a devil's food cake. All right. Devil's food cake has a couple of different acids in them. So we've got our chocolate, we've got the baking powder, but if when we neutralize it with the baking soda, the pH comes to somewhere around 7, so somewhere around neutral, because we have the extra alkaline in there. All right. Um, if we left it with just baking powder, which is baking soda and baking acid, the pH is a little bit less than 7, so we end up getting something that's bleached. All right. So devil's food, because it has baking soda and baking powder, we neutralize that, making it having less acid available. We are able to retain the color. So we get that nice dark mahogany color. Whereas if we only left baking powder, baking soda, and the acid, it does bleach it and we get something almost rusty colored, kind of like our chlorophyll. If we're doing string beans or broccoli and we add lemon juice. All right, we don't want to bleach it. Other acids that we're going to be working with, we have our buttermilk, we have sour cream, cream of tartar, all right, vinegar, chocolate. Chocolate is interesting. Chocolate is considered acidic because it's around 6.7, 6.8 on the pH scale. But remember, that's still less than our neutral 7. We have molasses, brown sugar, and of course, fruit juice. So when you're working with your baking soda, all right, the general rule of thumb is 1/4 teaspoon of baking soda per 1 cup of flour to get that chemical reaction started. Baking powder is our baking soda, sodium bicarbonate plus our acid plus starch. All right. So baking powder plus liquid will give you your CO2 reaction. All right. I'm pretty sure you guys did this when you did your quick breads foods lab. You guys tested out the reaction time and the amount of aeration that you get with your baking soda, baking powder, and different temperatures as well. Your double acting baking powder, it does react twice. Number one, the first one, it happens when when the baking powder is moistened. All right, so when you incorporate it into your dry ingredients and you put the wet ingredients into it, you do get some CO2 reaction. And then when you put it in the oven, all right, that's when you get the second burst of CO2 production. So substitutes for when you're substituting baking soda for baking powder, all right. A lot of times we do have this in it's one of our pantry items. What you can do to create baking powder is use 1 teaspoon of baking powder plus half a teaspoon of cream of tartar, all right, and a little bit of cornstarch will get you baking powder. All right. So the rule of thumb, 1 to 1.5 teaspoons of baking powder per 1 cup of flour if you're going to work on your own recipes. Biological leavening, we do have our yeast again. So we have our yeast that we combine with some sort of food source, liquid and warm temperatures, and that'll get you the CO2 because you're hydrating the yeast and you're giving it some sort of food. So you get these bubbles over here, the CO2 bubbles. We can also aerate with air. All right. So how do we get air into our flour mixture? You can do it by beating the batter, all right, using your stand mixer or your hand mixer to incorporate air into the flour mixture. We can also do the process of creaming. Creaming is when you take fat and sugar and you mix it together, okay? You can get some height off of this. How this works is we're using the plasticity of the butter. You want to keep the fat nice and cold. So when you go in there with the hand mixer, you're stretching out the fat, you're taking advantage of the plasticity. It surrounds the granule of sugar. And when you incorporate it into the recipe, what happens is that sugar is going to get mixed into the recipe, but it's covered in fat. And when you add heat to fat, what happens? It melts away, and then you end up with a void inside your crumb. Okay. The other way that we can add air into our mixture is by sifting the flour. All right. You're literally going in there, you're breaking everything up, breaking up any of the clumps, and you're gently, all right, it's gently mixing in the other ingredients. So you get something that's not as dense as packed flour. So how does sugar help us? All right, when we're using sugar, sugar has a couple of different uses when we're cooking with it. Number one, yes, it is a sweetener. We can also use it for browning, getting that nice color. We get the caramelization. If we're working with proteins, we get that Maillard reaction. Both work with dry heat. It also works as a tenderizer. So remember, let's go back to our formula for gluten. Gluten, we need the smaller proteins, gluten and gliadin. We also need liquid and manipulation. Sugar loves to steal liquid and make it part of its molecular makeup, right? So it steals it and makes it inaccessible for anyone else. It steals it and it takes it away for good. So it competes for the liquid. As long as sugar's in there, whatever liquid you're putting into your flour mixture, it will steal part of it. Think of fiber or bran when we're making our rice. The extra fiber requires softening, which requires on its own extra liquid. Sugar does the same thing. So it competes for the liquid and it does act as a tenderizer because it's taking away the liquid required for our gluten production. It's also acting as as food for the yeast. All right, it's the simplest of things. Sugar is we can looking at sucrose, looking at maltose, looking at anything. It does feed the yeast, and the yeast uses that to metabolize and make it into CO2. Sugar also, because we're adding solutes to our liquid, right? It increases the cooking temperature needed to achieve gelatinization, all right, and our coagulation. Um, that being said, because it steals sugar, sorry, because it steals liquid, it does increase moistness for all of our baked goods. So it delays staling because it's part of it takes the water or the liquid as part of its molecular structure. It delays staling by holding on to that liquid. So the starches and the proteins aren't releasing liquid. Sugar also influences the volume of a yeast bread loaf. All right. Yes, it provides food for the yeast, but it makes the network a little bit heavier. All right. So it decreases the volume by the weight and it makes it a little bit stickier. It does compete for the liquid, but it also causes dehydration and death of the yeast cells. So you're not going to get optimal CO2 production. Look at these different loaves over here. We have 0%. This is the nice height that we get from just the mixture that we made without any sugar, 2%, 5%, 10%, 20 and 30%. This is all by weight. All right. It does add pressure to the protein network that we're trying to create and trying to hold on to, trying to cook off. So we are going to end up with something a little bit more dense. Yes, sugar is good. It gives a light flavor, but molecular weight, it is going to be heavier. All right. When we're looking at salt, salt, we all know, is a flavor enhancer. It does contribute to flavor. However, it does affect it does affect the gluten that we're making. So it firms the gluten because wherever salt is, water follows. All right. So it can make the dough more elastic, but too much salt, again, is going to um, dehydrate the batter or the dough that you're making. So you want to make sure you're actually using the proper amount of salt to improve the volume, texture, and the evenness of the crumb. What we have over here, we have this dough that was kneaded for 5 minutes. Um, it's pretty much breaking apart, whereas this one with the optimal amount of salt, you can see the little window. This is what we call this. You want to be able to stretch the dough. All right, this is how you know you've made the proper amount of gluten. You can see light through it, but you can't see directly through it. You're also not getting the holes like we have over here. Too much salt will kill your yeast. All right. We do have, like I said before, yeast is a living organism, is a one-celled organism. Salt will burn it, and it also steals the water. All right, so it does dry out, which can work in our favor in the future. So too much salt decreases the CO2 production because it kills the yeast, and it also decreases the volume of the loaf because we're not getting optimal fermentation. We're not getting the proper amount of CO2 that we're looking for here. Now, fat. Fat is also called a shortener. All right, it's shortening. All right. How does it shorten? Let's go back to our gluten formula. What do we need for gluten? Glutenin, gliadin, liquid, and manipulation. What fat does is it covers or it coats the smaller proteins, glutenin and gliadin, and makes them less available. So we're going to end up with something a little bit more tender. The gluten strands are going to be shorter, therefore, it's called a shortening. All right. So we can use oils or fat in two ways. Solid fats, when it's nice and cold, we use its plasticity to create a flaky product because it literally covers the other proteins, gluten and gliadin, and it gets between the starch strands that we're trying to hydrate, and they don't melt away until we add heat. So we get something that's nice and flaky. We can also call it, oh gosh, laminated. All right. Our liquid oil, think about going to the beach. If you've gone to the beach when you were a kid, you grab some water, you bring it back to make like a sand castle on the sand. It does give you a tender product, but it's not flaky. It's going to be more dense. All right. Fat is also used as an emulsifier. We looked at our unsaturated and polyunsaturated fats. They're used to emulsify our two immiscible or not easily mixed products, so we can evenly disperse the ingredients in the batter. As with plasticity, all right, remember we spoke about creaming. When you take your fat and your sugar and you mix them together until each granule of sugar is completely coated with fat and then it melts away during cooking. We also use fat to delay staling. All right. Staling is when any bread product or baked product starts losing water, it becomes very dry and brittle. By adding fat, we slow this down a little bit. So fat as an emulsifier, we can see how the mixture worked over here. Without the emulsifier, we can see how the bread was rolled, how it was kneaded, how it was formed. We can also see these tunnels over here. This is where the fat melted away and it wasn't mixed with the water. Whereas over here, we still see how the dough was kneaded and shaped before it was panned. But there's not as many holes, not as many voids over here. So it does, when we mix it properly, it does improve the shelf life. So how do we use our liquid in our flour mixtures? All right, liquid, the function of it, number one, is to hydrate the starch, help with gluten formation, and to help dissolve ingredients. We also use liquid to create steam. So steam, again, remember we're adding air to our mixture. We use it as a leavening product. As soon as it goes into a 425-degree oven, we know water boils at 212. We get that leavening. So we can get that from our eggs, milk, fruit juices, and water. As far as eggs go, we do incorporate air when the eggs are whipped or beaten. All right. When we're using some sort of foam, especially you guys will see this when you look at your angel food cake. And we also use a liquid from the eggs to hydrate the starch and the proteins for gluten formation. It helps us provide structure when we get that mostly from the egg white or the albumin. All right. Think of using it as a binder. All right. We take use of the lecithin from our egg yolk. All right. That's our emulsifier. That's our most commonly used phospholipid. And of course, it adds flavor, it adds color from the egg yolk, um, color from the uh, the Maillard reaction with the dry heat and the protein. It also adds extra nutrients. So we have extra calories, we have extra protein in there. We can make a high protein bread depending on how much eggs we use. All right. So, that being said, let's move on to our physical flour mixtures. All right. This is a really good slide to study from. We have four types of flour mixtures that we're going to be looking at. Number one, the first category, we're going to look at doughs and batters. As far as doughs, we have our stiff doughs and our soft doughs. We'll get into those. And then batters. We have drop batters and pour batters. All right. As you guys can imagine, pour batter is something that you can actually pour. So you put it into a pitcher. If you think of your pancakes, all right, that you've ever made, popovers, waffles, those can easily pour. It's basically a 1-to-1 ratio as far as dry ingredients to wet ingredients. So let's get into these. So our doughs, all right. We have soft doughs and firm doughs, all right. Our soft doughs are a 1-to-3 liquid to flour ratio. So for every 1/3 cup of liquid, we have 1 cup of flour. This we can knead, all right. Whereas our stiff doughs is a 1-to-4 ratio, all right. So for every 1/4 cup of liquid, whether we use milk or water or whatever it is, eggs, that is dispersed amongst 1 cup of flour. So it's a little bit tougher. All right. Both of these we can knead, but the soft and the firm doughs, most times we will use these for our yeast breads. They get handled a little bit differently. Pour batters are a 1-to-1 ratio. All right. We can literally put these into a pitcher and pour them out. Whereas drop batters, they're not thick enough to be kneaded, but we can't pour them either. Think of taking a spoon, putting the batter on a spoon. It will hold its shape, but you have to flick it off of the spoon and basically drop it onto the cooking tray. All right, so they are dropped. Too thick to be poured, too thin to be kneaded. All right. When you're storing these flour mixtures, all right, you want to make sure they're pest proof. Flour is a starch, it's a sugar, it's a food source. So bugs, rodents, everything will try to get into it. When you're dealing with white flour on its own, all right, you want to make sure that you store it in a dry place. You want to prevent the activation of the natural enzymes, and then your whole grain flour, because it has the bran and it still has the germ in there, you want to make sure to refrigerate it. It will go rancid if you leave it in room temperature. Your kneaded flour mixtures, if they're frozen, you want to make sure that when you defrost them in the refrigerator. All right. You don't want to throw them straight into the oven. You defrost them first, shape them, and then bake them. And then your extended frozen storage, if you're using frozen dough, it does have a short shelf life because remember what happens to water. When it freezes, it expands. When you bring it back to temperature, that protein network isn't going to be as viable as it was before. So the loss of dough strength will give you something that has a smaller volume because we are breaking down the gluten proteins when we freeze it. The commercial additives that we have dough conditioners. So these work to reduce the effects of staling. All right. So it improves machinability, it improves the volume. and it holds on to, these are chemicals that are added to hold onto the liquid after it's been cooked. All right. And then your reducing agents, it does weaken, it does soften, excuse me, the gluten development so you don't get something that's too tough. So, as far as machinability, you don't have to work it as much to create that gluten, and you will get something that's a little bit tender. Your oxidizing agent, it does whiten the flour and improves the functionality of the dough. All right. Because your oxidizing agents, it's basically like changing the pH. So your proteins are a little bit softer. And your emulsifiers just help you increase the volume of the shaped dough via fermentation because it does make sure everything gets mixed properly. So that's it for this chapter. I'm going to start new videos for yeast breads and quick breads, and we'll get into that soon. All right.